The reason why I don't like that is because in reality, none of these hypotheses are true. So, for example, with Newton's laws and Einstein's laws, I think physicists don't actually think that Einstein's laws are exactly true either. They're like, keep looking for the correct theory. So like, what does that mean, right? The probability is 99% that this is correct, but we don't actually think it's correct because we think there's some other model out there. Or what about in the year 1850? No one had Einstein's theory. There's only Newton's laws. So does that mean they had a 100% chance of it being correct then? So that's kind of weird, like that the posterior probability depends on what things are in the model.
What's up, everybody? Welcome to the Artists of Data Science podcast, the only self-development podcast for data scientists. You're going to learn from and be inspired by the people, ideas, and conversations that will encourage creativity and innovation in yourself so that you can do the same for others. I also host open office hours. You can register to attend by going to bit.ly/ADSOH. I look forward to seeing you all there. Let's ride this beat out into another awesome episode, and don't forget to subscribe to the show and leave a 5-star review. Our guest today is an American statistician, professor of statistics and political science, and the director of the Applied Statistics Center at Columbia University. He's earned a bachelor's in mathematics and physics from MIT and a PhD in statistics from Harvard University. He frequently writes about Bayesian statistics, displaying data and interesting trends in social science. He's also well known for writing posts sharing his thoughts on best statistical practices in the sciences, with a frequent emphasis on what he sees as the absurd and unscientific. He's done research on a wide range of topics, ranging from why it's rational to vote, police stops in New York City, social network structure, arsenic in Bangladesh, and radon in your basement, and pretty much everything in between. So please help me in welcoming our guest today, the three-time recipient of the Outstanding Statistical Application Award from the American Statistical Association, Dr. Andrew Gelman.
I'm happy to speak with you.
So Dr. Gelman, talk to us about how you first got interested in statistics and what drew you to the field.
When I was a kid, I was always interested in math. I did some things like math team and math Olympiad competitions. Well, I found out that there were people better than me at that. And as a student, I didn't really know about applied math. So we just got the impression your mathematicians grow up and prove theorems. I majored in math and physics in college, but I don't feel that I had a great understanding of physics. I think it's very interesting, but I don't feel I had a great intuition. And then I ended up taking some classes in probability and statistics. So I ended up doing that, which is very appealing because you can work on so many different problems. I guess if I had known that mathematicians can work on lots of interesting problems, maybe I would have ended up doing that.
So how much more hyped has statistical and machine learning become since you first broke into the field?
Oh, well, it's much more high. We've already passed peak statistics. So maybe peak statistics might have been around 2010 or so. But then now I think machine learning obviously it's very related to statistics. It's kind of the same. Statistics is related to applied math. Machine learning is related to statistics. You can't really draw sharp lines, but these ideas are much more out there than they were when I was your age.
Yeah, well, actually, when I was in grad school, the class I took was called Statistical Learning, and it was before it was rebranded as machine learning. So yeah, you're right. The lines are really, really blurred between the two now. But I'm curious. So we've passed peak statistics. We're into the age of machine learning now. Where do you see the field of statistical and machine learning headed in the next 2 to 5 years?
2 to 5, I guess kind of more of the same, people solving bigger problems. One thing that we sometimes like to say is that big data need big model, because big data are available data. They're not designed experiments. They're not random samples. Often big data means these are data measurements you already have, not measurements of what you want to learn about. And so there's a need for more modeling. You need to adjust for differences between sample and population, differences between exposed and unexposed groups. Obviously, we've been hearing a lot about that lately with all the vaccine talk. And then differences between measurements that are available data and the underlying constructs of interest. So we want to use more data. To use more data, we need more model. So there's more of the same, being able to fit models faster, having better algorithms, more scalable computing, learning what works and what doesn't work so that we can build models and build algorithms that work better.
And so you've had your hands in a bunch of different problems. You've dabbled a little bit in everything. So I'm curious, what do you think the biggest positive impact machine learning will have on society in the next 2 to 5 years?
Oh, I don't know. I don't really know everything that's being done, right? Like, I don't know if when they're building these coronavirus vaccines, how much statistics or machine learning is being used and how much of it is sort of the kind of computational biology. Obviously there's a certain amount of math involved and a lot of technology. Then there are things that change our lives, but maybe not in such a good way, like the security cameras. I mean, maybe that's good, maybe it's bad, but I guess it's probably good that they can catch criminals better, but maybe bad if they can monitor you if you're doing something you don't want to be doing and so forth. So there's a lot of those problems. I guess these self-driving cars, I don't know that that's going to make so many people happier, but that presumably that will eventually come. A lot of sort of straight technological challenges.
So for those of us that are practitioners of machine learning and data science, what do you think would be some of our biggest concerns in the future?
What do you mean concerns? Like things you should worry about, or things like you want to learn because otherwise you're missing out? Or what do you mean by concerns?
I guess by concerns, I mean kind of like moral or ethical concerns.
It's hard to anticipate these things. I mean, there are obvious things like people can use math, applied math, statistics, machine learning to build more effective weapons. So that's a concern, right? I mean, weapons aren't always used by the good guys. And some of the methods, the statistical methods that we use, the methods in probability theory that we use, some of them were invented by Stanislav Ulam to build the H-bomb. Now, you might argue the H-bomb was a good thing. Maybe it's prevented some wars. I'm not sure. But if someone in the lab is trying to use statistical methods to build a very compact and dangerous bomb, that would be horrible, right? So that's probably the biggest thing. And then we talked about surveillance, which can be used to stop bad guys, but of course it can also be used by powerful people to suppress less powerful people. I guess those are two obvious things to worry about. I guess people are also worried about what will happen to the economy if nobody has a job. I don't quite know how to think about that. It's harder for me to have a reaction to that one way or the other.
Well, thank you very much for your inputs there. So I saw this really awesome lecture you gave at the University of Vienna on Bayesian workflow. I think our audience would really love to hear you talk about that and kind of dig into that. So kind of just at a high level, first question here, what do we mean by Bayesian?
So Bayesian means it uses the mathematics of probability theory to do inference, to learn. And Like the math is some formulas, but it looks different in different applications. But usually, typically, the key idea of Bayesian inference is, well, there's a few things. One is the idea of capturing uncertainty using probability, so making statements that this is the odds that this might happen. The second is combination of information from different sources. And the third, which is related, is what we sometimes call partial pooling, which means you use some of the information from one source and some from the other. For example, when we're doing election forecasting, there's presidential election coming up, we have two pieces of information. One is the forecast from the political and economic fundamentals. And so that can be whatever you want it to be, but includes incumbency, it includes presidential popularity, includes measures of the economy. So based on that, you have some sense, well, the economy isn't going very well, the president is not popular. They put this together, it suggests a bad outcome for the incumbent party. But there's uncertainty, so we can estimate that uncertainty based on past elections. So sometimes that's called the prior distribution based on prior information. The thing I'll emphasize here is this prior distribution is not a subjective or made-up number. It's actually a statistical model fit to data. Then we also have direct data. We have polls. Well, polls are indirect data because even if a poll is perfect, it's a snapshot, not a forecast. So we have three things. We have our forecast based on the fundamentals. We have our polls with a model of the polls where they're aiming to estimate public opinion now. And then we have a time series model of the latent process, the unobserved process of public opinion in the 50 states as it varies between now and the election. So a lot of Bayesian models have this feature that you're combining different sources of information. Another example would be drug development. So you have measurements of, you give someone a drug and you have some measurements of the concentration of the drug at different times, maybe in their blood. Then you also have prior information about how the drug will work based on the distribution of past drugs. And then you have a statistical or mathematical model connecting these. So you have to have a model with all these parameters representing the flow of the drug. So I didn't say anything about workflow, but that's kind of the essence of Bayesian.
Yeah, definitely. We'll get into that workflow bit. But before we jump to that question, I'm curious, so what's like the main difference between the frequentist and the Bayesian?
I think we say that like frequentist refers to a method, approach to evaluating statistical procedures. Bayesian is a method or an approach to come up with a procedure. So frequency evaluation would say, if I were to apply this procedure many times, how would it perform? And I think about that as a textbook writer and as a developer of software that has defaults. So I'm very interested in how things will work. We rarely do things just once. We apply our procedures over and over again. So the frequency properties are important. So I would say they're both important. Bayesian is a very useful way of combining information. Frequency evaluation is a good way of understanding our procedures when they're applied repeatedly.
So let's get into workflow now. So what is a workflow?
So workflow is this phrase, I think it maybe comes from computer science or engineering. In the past few years, it's entered statistics, partly through the R community. So R is this piece of software that we all use in statistics and we all kind of hate. It's like the software equivalent of the English language. It just seems to do what's needed, but it doesn't have that nice Esperanto feel. It may get supplanted at some point. But one thing that the R community has been very good at, and Hadley is just one of many people in that community, he's been particularly innovative, they've been very interested in what we actually do, what statisticians do, what data analysts do, what data scientists do. Most statistical theory isn't so much about what people actually do, it's much more theoretical. So when the so-called tidyverse is all about how to clean data, work with data, analyze data, and they were thinking a lot about workflow. So then a few years ago, we in the Bayesian community started to adopt this view, and we started to talk about Bayesian workflow. I think 2016 was the first. I'm writing an article about this now, and we were planning to write a book about it. And I think that, so I was looking stuff up, and I think 2016 or so was the first example I could find of Bayesian workflow. But workflow is about what we do and how it's different from what we talk about. So what we talk about is inference, and we do inference, but we don't just do inference. We do model building, we do debugging, we add data to our models, we add new kinds of data, we snap things in, we do unit tests, we simulate fake data, we look at our inferences and see whether they make sense. So I've been interested in that. I've been thinking that it's good for us to shine the spotlight on some of these activities and try to formalize them to some extent. And the thing that I've been most interested in lately is the idea that we fit multiple models. And in statistical theory, they talk about model selection and model averaging. So you fit multiple models, which is the best, or let's average over them. But that's not quite what I'm talking about here. What I'm talking about here is that I fit multiple models as a way of understanding things. So there may be a model I want to get to, which is like step 10 in the process. I fit models 1 through 9 because I'm not going to understand model 10 if I start with it. But it doesn't mean I'm trying to choose between the 10 models or average over the 10 models. I like the last one the best, but I have to kind of work my way there. Similarly to engineering, right? You would not build a bridge straight up, right? You'd build little bridges, and even the final bridge you build in pieces. But if you look at statistics textbooks, including my own, they tend to present models as just existing in their entirety, like the so-called the Greek god or goddess who sprung from the head of the other god, whatever, like that idea. Or like the night when people think about cloning and they don't realize that if you want to clone yourself, then you have to wait 30 years for the clone to grow up.
So when you talk about models 1 through 9 and get to model 10, we're not averaging the models. So what are we doing with models 1 through 9? Are we using that kind of as a discovery, or are we kind of iteratively fitting more and more models?
We are fitting more and more models. A lot of the models we fit are bad models. A lot of the models we fit, we're not planning to. There's two kinds of bad models. So one kind of bad model is just if there's a bug. Like I was fitting a model for coronavirus tests, and I switched the sensitivity and the specificity parameters in my model. Like it just gave the wrong answer. It was an actual bug. You have a typo, right? Like something like that. So a lot of our models are wrong. But then there are models that they're not bugs. They're not mathematically wrong, but we know they're incomplete. Like we have a model we're comparing treatment and control group in an observational study. And so we start by comparing, and then we adjust for one variable, and then we adjust for another. And we know that the first three variables we adjusted for are not enough. We didn't adjust for age, right? Then we adjust for age. We forgot to adjust for smoking status. Well, we adjusted for smoking status. Were you ever a smoker or never a smoker? Well, that's not enough. You have to do more. So we're building a sequence of models knowing that we haven't done enough. They're bad models. They're the wrong model, but we have to get there. So it's not like we don't hold our breath until we're at the final stage. And it's funny, it's like these things don't always get published because you publish the final step. You don't publish everything that came before, right?
So how does the Bayesian workflow differ from the frequentist workflow?
There are particular steps. The Bayesian workflow involves probability calculation. So it involves certain math or certain computer programs that we use. In the frequentist workflow, you have to come up with an estimator. The frequentism doesn't tell you where the estimator comes from. Like you could use a Bayesian estimator, you do something else. So in the frequentist workflow, you kind of have to develop an estimator and then work out its theoretical properties. In the Bayesian workflow, you don't have to do that. So the Bayesian is easier in that sense because that you just have to give your assumptions and then everything goes from there. Of course, then you need to check your assumptions.
So why is it that what makes a statistical method effective is not what it does with the data, but what data it uses?
Oh, that's Hal Stern's quote. I love saying that. So machine learning, why is machine learning, one reason it's so great is because they just say keep throwing in features. Like, oh yeah, we can handle that. So they use regularization, which means they fit huge models, but the fitting is done. They don't take the best fit to data, they cross-validate. And that's not the way Bayesian does regularization in other ways by using prior distributions, but it's the same idea. So like if I should just give you an example, we're doing election forecasting and we have two kinds of polls. So some polls adjust for party identification and some don't. It's better to adjust for party identification because if you might have a survey and it looks like Trump is doing well, but you just got too many Republicans in your survey. But not all surveys adjust for party ID. It's more difficult because there's no census on party IDs. You have to make some more assumptions. So we're putting these polls together. How do we deal with this? You could just use one kind or the other. We use both, but then we fit a regression model and we say that our baseline are the ones that do adjust for party ID, but the ones that don't adjust for party ID provide some information, but they have a bias. The bias is allowed to change slowly over time. Another example would be when we did our analysis of radon in your basement. We had data from different surveys, and one survey was a small sample, only 5,000 houses, but the measurements were accurate and we believe unbiased. The other survey had 80,000 measurements, and the measurements were much more noisy and they had different levels of bias. What did we do? We included all the data. We modeled the bias and the variance of the bad data. So we allowed the model to partially pool or use that information. That's an example where Bayes can work very well. It would be kind of hard to do that using a machine learning approach. That said, I can't use Bayes to write a computer program to play ping pong. The machine learner people can do that. So they're great. And there's room for everybody.
So why do Bayesians then tend to be a little bit more skeptical in their thought processes?
My experience with Bayesians, it's changed. So I'm glad to hear you say that, because when back in 1991, I went to a Bayesian conference and I was going to all the talks and asking people if I wanted to see simulations from their models and see whether the simulations made sense. And people were all saying, no, these are our subjective models, so you can't check them. And if they're subjective, then you should really want to check them, right? No, you don't understand. Well, I understood. Anyway, there was a kind of philosophy. So Bayesians traditionally, in the old days, had an aggressively anti-skeptical philosophy. And I would say that classical statisticians were considered very skeptical. They only believed things if they were statistically significant. So it's good to hear what you're saying. I like that. I like to think that Bayesians have the reputation of being the skeptics now.
So I thought this quote was really interesting from the talk that I referenced above, which I'll definitely link this talk into the show notes as well. But you had a quote that said, your method of evaluation can be inspired by the model, or the model can be inspired by your method of evaluation. I was wondering if you could just elaborate on that.
Well, there's a saying that to understand the past, we must first know the future, right? You've perhaps heard that. And so similarly in statistics, this is a commonplace in experimental design or data collection. If you design an experiment, you want to know what you're going to do later. So, well, most obviously, you want your sample size to be large enough so that given the effect size that you expect to see, you'll get a strong enough signal that you can make a strong statement. There's no point in doing a study if your standard error is going to be bigger than your estimate. So that's part of it. But then even deciding to do things like random assignment or blinding or whatever, a lot depends on what outcomes you're interested in. Right? So I think if you, in some morally speaking, it's almost immoral to gather data or do an analysis without knowing how you would evaluate it. It would be, when I say immoral, I'm purposely making too strong a statement, but the example would be education. So we're always trying new things for our classes. Strictly speaking, I don't live up to this myself, but I should never do an innovation without having a plan for evaluating it. I should have a pre-test for my students and a post-test and some comparison of who gets the innovation and who doesn't. I don't usually do that, but that's bad. And I don't get the most use out of my innovations. Imagine if you decided you wanted to lose some weight or maybe gain some weight, and you thought, well, different days I'll do different things and I'll see what happens. It'll be impossible to keep track. You have to at least record what you've done. This is really fundamental. So when people talk about experimental design, they talk about sample size, they talk about randomization, double blind. There's more fundamental things like that. It's actually record what you did and record your outcome that you're interested in. Well, you have to decide what you actually care about. So that's why you should really always have an evaluation plan, even though we don't. You probably did not for your podcast, but in theory, you should.
Yeah, I spent a good chunk of my career as a biostatistician. We always had these statistical analysis plans that would, in the real world, it's not always that nice and neat, but yeah, we'd have these statistical analysis plan laid out, how we're going to design the experiment, how we're going to conduct it and everything. And when I transitioned into data science, no such thing. It's just like, here's the data, let's figure some stuff out and do stuff with it, kind of doing it the quote unquote backward approach. But yeah, thank you for your insights on that. So there's a really interesting paper that you co-authored called Philosophy and the Practice of Bayesian Statistics, which is actually how I first came across your work. I'd just love to dig into it just a little bit. So you open fairly early in the paper talking about the usual story for Bayesian statistics. So what is the usual story when it comes to Bayesian statistics, and why don't you like it?
Well, the usual story may have changed, but the usual story is that as it has sometimes been framed, I think it's still maybe that way in Wikipedia, is that there are different models of the world. For example, you have maybe Newton's laws are correct, or maybe Einstein's theory of relativity is correct. So you might start with equal 50-50 prior on them. You might say either one of these two models is equally likely to be correct, and then you gather data. And you eventually see that the data are consistent with Einstein's theory and not Newton's theory, so therefore the probability of Einstein's theory approaches 1 and the probability of Newton's theory approaches 0. Or you have just any kind of situation like that. There's debates about global warming, and so people have different views, and as you gather more views, you eventually get enough evidence that one hypothesis or another ends up being dominating. And the reason why I don't like that is because in reality, none of these hypotheses are true. So, for example, with Newton's laws and Einstein's laws, I think physicists don't actually think that Einstein's laws are exactly true either. They're like, keep looking for the correct theory. So like, what does that mean, right? The probability is 99% that this is correct, but we don't actually think it's correct because we think there's some other model out there. Or what about in the year 1850? No one had Einstein's theory. There was only Newton's laws. So does that mean they had a 100% chance of it being correct then? So that's kind of weird, like that the posterior probability depends on what things are in the model. So this is really related to George Cantor's paradox or diagonal argument, that there's always going to be another theory out there that you only think about because of certain experimental data. Philosophers of science like Popper and Kuhn we're very aware of this, that a theory suggests experiments, but data gathering experiments create anomalies which suggest the need for new theories. And the classical Bayesian approach, in which you have a fixed number of models and each has a probability, that does not capture that. It's very limited. Now, at this point, you might say, well, that's fine. Let's just have another, I might have 2 or 3 hypotheses. I'm going to create a third or a fourth called everything else. And I'll assign prior probability to that. The trouble is that won't work because your Bayesian updating can't work with a theory that's unspecified. The everything else model has to actually itself be a full model of the data, or else you can't update its probability, which means you can't do any of the other stuff. So I think it's a kind of internally coherent theory, that the traditional Bayesianism is an internally coherent theory that doesn't really describe science. And I was bothered by it. This came up, why write a paper about philosophy in the first place? And I was bothered by it for 2 reasons. So one is that if you're not Bayesian, you might say, well, I don't want to use these Bayesian methods because it's based on this ridiculous idea of having a probability on a hypothesis. So I'm going to say, well, you don't need to do that. But then the other is that Bayesians, as I alluded to earlier, used to often have an aggressive attitude of not wanting to check their models on the basis that if they checked their models, they would lose coherence. And so I was arguing that you can't really have coherence, that every philosophy of science has some leak in it. So I wanted to, one reason that we wrote this, that Cosma Shalizi and I wrote this article, was to kind of try to free the Bayesians from that. And there are particular methods that Bayesians were using, like Bayes factors and certain things that I think were actually giving bad answers. I wrote a paper in 1995 about this in Sociology Journal, where I think people were sometimes just getting wrong answers because they were using these methods that were inappropriate.
What's up, artists? I would love to hear from you. Feel free to send me an email to theartistsofdatascience@gmail.com. Let me know what you love about the show. Let me know what you don't love about the show. And let me know what you would like to see in the future. I absolutely would love to hear from you. I've also got open office hours that I will be hosting, and you can register by going to bit.ly/ADSOH. I look forward to hearing from you all, and I look forward to seeing you in the office hours. Let's get back to the episode. So talking about philosophy, why should statisticians and data scientists care about philosophy?
Well, there's that quote from Keynes about that people, what is it? Like that people who think they're exempt from philosophical influence are actually the slaves of some long dead. Do you know what I'm talking about? There's a quote, the ideas of economists and political philosophers, both when they are right and when they are wrong, are more powerful than is commonly understood, said Keynes. Indeed, the world is ruled by little else. Practical men who believe themselves to be quite exempt from any intellectual influences are usually slaves of some defunct economist. So the alternative to good philosophy is not no philosophy, it's bad philosophy. Philosophy will fill in the vacuum. And I see this all the time. All the time, people use a method and their justification for their method is a non-existent theorem. They'll say, oh, well, this method, I remember this in 1995 when my colleague and I wrote this paper, because we were responding to another article and the person said how a certain procedure would work better, like give better predictions or something. I don't remember exactly what he said. But then we just shot back, why are you saying that? There's no theorem that says they'll give better predictions. There's no evidence for that. You just think it because it's like a good thing. You think good things go together. It doesn't work that way. So you have people in statistics or in econometrics using what they consider unbiased estimates. Well, they're not unbiased if you select on statistical significance, which you do. It's just, they're not, right? But people just think they're good, or it's maximum likelihood. So that's your default method. Well, one of the things I love about machine learning is that that's moved people away from that because they're starting to realize machine learning is not called Bayesian. So the non-Bayesians are starting to accept that something other than maximum likelihood can make sense. Or Bayesian saying they're using a subjective prior and that was coherent, right? That was the thing. So that was kind of the purpose of that article. So our particular article did not resolve all philosophical issues, but I think it's very important to write about philosophy because it's there, it's unavoidable.
Definitely. I thought it was a really well-written article. I'll be sure to link that into show notes as well. So speaking about, you mentioned maximum likelihood, you mentioned significance, something closely related to that, p-values. What the heck is a p-value?
The p-value is if you gather some data and you have a certain statistical model called the null hypothesis, the p-value is the probability of seeing something at least as extreme as your data if the null hypothesis is actually true. So the example that we'll give in class would be, let's say somebody is shooting baskets and he or she takes 100 shots, and you have a null hypothesis, which is that their shots are independent and have equal chance of going into the hoop. So then you might do something like fit a linear regression of the success rate over time. And if the slope is positive, it means the person's getting better. And if the slope is negative, the person's getting worse. And I think most people, even professionals, will actually improve if you get them to take a bunch of shots. Maybe after 100, they'll get tired, but that's another story. So you can run this regression and estimate this slope, which represents your improvement or decline. And then, or you could do the math, or you can do simulations, and you can say if this person were actually shooting with equal probability and each shot was like a new draw of a ball from an urn, as it were, you can look at the possible slopes, regression coefficients you might estimate, and you'll see that there's a range that you'll see. There's a distribution of them. And you do it and you see a certain slope and you can see where it is in the distribution. The p-value is the area of the distribution that's greater than or equal to the slope that you actually see. And if the p-value is low, like very close to zero, then that suggests that your null hypothesis or your random model of the data is flawed. And if the p-value is kind of near 50%, then that suggests that the data can be explained. Not that this null model is true, but that the null model cannot be refuted in this way. It's a kind of very interesting way of thinking about the world. It's an indirect form of reasoning.
So kind of a tongue-in-cheek question here based on some research I did. I can't remember if it was the title of your article or if it was the subheading in one of the articles, but how can we solve all of our statistics problems using p-values?
Oh, yeah, I think that I gave that the title of my talk. That was being ironic. I think we can only solve some problems. So it's sometimes said of the p-value that you can only reject a model, you can never accept it. But paradoxically, you can learn more from a p-value when you don't reject it when you do, because when you reject, you say that your model is false, but you knew your model was false. If you can't reject, then it says you don't have enough information to make the call. But it solves some problems. So you could see, like in that basketball problem, like you can say, oh, I have evidence that people's ability really is not constant. So then you can kind of move forward from there. You've refuted this. Or you can say, I can't refute the null hypothesis that the ability is constant. Well, that's interesting. You can say that too. It's useful to the extent that your null model is useful. And if your null model is uninteresting, then it's not interesting to reject it.
So is there a difference in interpretations for p-values between Bayesian and frequentist?
The interpretation is what it is. What are you going to do with it is the question. If you're going to say that when the p-value is less than 0.05 or 0.01, then you publish a paper, that's like not, there aren't really any principles of decision theory in which that's a sensible decision process. It's something that people do. It's part of statistical workflow, but I think it's caused a lot of damage. But it's kind of outside of the interpretation of the p-value is what it is. It's like if you're using it to make decisions is the question.
So do you feel like the p-value is a difficult concept for a lot of people to understand? And if so, why do you think it's a bit challenging?
Yes, I have a paper that misdefines the p-value myself. Well, I wrote this paper as somebody, and it was for a magazine, not a journal, and magazines will like clean up your writing to make it more readable. So they cleaned it up and made it more readable and wrong, and I didn't notice. So forever now, people can find this and say, even Gelman, blah, 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 also didn't understand. Well, I understood, but I didn't read it carefully, and so it's on me. After all, it's under my name. Yeah, it's complicated because it's a function of the data, but it depends very much on this null hypothesis, this model of the world. And I think people aren't always aware of that. There's usually a lot of assumptions baked into it that aren't there. And people will, a lot of quotes from textbooks where the p-value is said to be the probability that the model is true, or the p-value is, there's kind of a whole bunch of misunderstandings of it. And it does seem like when people misunderstand something that many ways, it obviously is tricky, right?
Yeah, I like that's the function of the null hypothesis and the data, and not really a statement of confidence or probability, really, right?
Right. Well, it is a probability statement, but it's an indirect probability statement.
Yeah. So I heard a talk that you gave at an R conference, solve all your statistics problems using p-values. And you went on record and you're saying that the least important part of data science is statistics. So I was wondering if you could talk about that, what you meant by that.
Well, I do statistics. It's the least important part, but like somebody has to do it, right? I can't remember exactly what I said on this, but mainly like data quality is more important. And that's the big thing. So you can't really do stuff if the data are no good, and if your computing is such that you can't even grab all the data, if you're limited by what data are available. So when we're working with polls, we're mostly using reported results from the pollsters when none of the raw data. So there's a limit to what we can do. No matter how much statistics we have, it's not as good as having the raw data. And of course, you've heard about this with coronavirus, that there are tests of people, but it's the people, they don't really know so much who's being tested, and They don't have a lot of data on the negative tests. So if the data aren't that good, then again, you can try to salvage things with statistics, but it's not the most important part. So the data and then the theories, right? Of course, all the statistics in the world are not going to give us a single vaccine, right? So the science is it's important. Statistics is in there to help evaluate it, but that's not the most less important. But it still matters. It's not nothing. And sometimes the importance of statistics is a kind of negative importance that if you know statistics, sometimes you won't be fooled by bad statistics. So you'll see something and you won't get snowed by it.
Awesome. Thank you for that. Yeah, I was looking forward to get you to talk about that because I thought it was a pretty interesting comment you made there during that conference. So you study a lot about voting, political system. So why is it that Americans vote the way they do?
That was such a bad title for a subtitle for a book, like as if we can answer why people do. Why is a funny thing. Why is a question. It's never an answer. We wrote, Guido Imbens and I wrote this paper, Why Ask Why, about that. We said, you ask why. So when you ask why, that implies that there's an anomaly, there's something you don't understand. So by asking why, the implication is that there's a model of the world that you have, and then there's some reality that doesn't fit the model. And so you're trying to understand that. So I guess for voting, it's usually people are puzzled why anybody votes for the other party unless they're like completely corrupt or whatever. It seems bizarre, right? Why are these people voting for the other guys? They're so bad. You can't answer why. You can only ask the question, but then you can look at various comparisons. So we found it's that. Well, back then, so of course, white people vote more Republican than ethnic minorities in this country. Richer people vote more Republican than lower income people, but that's actually much less than it used to be. So it's changed. That it is kind of interesting, something not that well understood, that the parties are actually in many ways more polarized on economic issues than ever before. And yet we see a very small difference in how richer and poorer people vote for Democratic and Republican parties. We found that this varies regionally, and in the Northeast, there was very little difference between how rich and poor people voted. In the South, richer people were much more conservative, much more Republican voting than poorer people. So it varies by where you are in the country. And we were picking that out at different ways. People who attend church more often are more likely to vote for Republicans. But that difference between church attenders and non-attenders is a much bigger difference among richer people than poorer people. So if you're higher income voters, that's another way of saying that. The difference between Republicans and the cultural differences between the two parties are much more pronounced at the higher end of income than among lower income voters.
Awesome. Thank you for that. Hey, so last formal question before I jump into a real quick lightning round here, and that is, what's the one thing you want people to learn from your story?
I'll say what I learned from other people's stories. So why did I go into research? Because when I sort of statistical reasoning, is before I was a statistician, before I'd even taken a statistics class, I was trying to figure out what to do when I grew up. And I knew I was good at math and stuff. So it was a different era. Like I think now people like want to get rich. So when I was a kid, nobody wanted to get rich. I mean, people, we wanted to get good salaries, but getting rich was not an ambition, which is good for me. It didn't come up. I'm comfortable. I'm doing fine. Your readers don't have to send me, money or whatever, but that wasn't my goal. So, but I wanted to contribute to the world and I knew I could in some way. And I looked at like older people, like men and women older people's parents and people I worked with. And I noticed that the ones in research, not just at universities, but like I also worked in government research lab during the summer, the ones in research seemed to enjoy their jobs. And when the people I knew who weren't in research, like including my own parents, and I mean, they had pleasant mid-level white collar jobs, they were doing fine, but they did not enjoy their work in the same way. They did some useful things. It's not that they hated their jobs, but so I thought I want to do that. And also when I grow up and have kids, I want to be able to have time to be with my kids. And so I'm lucky enough I could be a professor. That's a good job because I have flexible hours and I can do research. So what people can learn from my experience is maybe that you can learn by thinking of yourself as one from a larger sample. And so look at other people like you and think of your options, and then think of like what they're doing in their 50s and how they're liking it and how it works with their families and so forth, and let that guide you a little bit.
I absolutely love that. Thank you very much for sharing that. So jumping into a quick lightning round here. If you could meet any historical figure, who would it be and what would you ask them?
Maybe I'd talk to Laplace or Ulam, and I would talk to them about all the problems I'm trying to figure out and see if they could probably help me out and figure out a lot of them for me. That's what I would do.
So what do you believe that other people think is crazy?
What I think is that we have a bundle of beliefs, and if you look at people carefully enough, you will find places you disagree with them. And my colleagues, Sharad Goyal and some other people, did a study a few years ago on Facebook where they asked people some questions about themselves. And then they also asked what they thought their friends would respond to these questions. And then they asked the other people so they could find out what people thought about their friends. And they found out, roughly speaking, that people agreed with most issues, people agreed with their friends on, but not as much as people thought they would agree. That is, like, people agreed with their friends about 70% of the time, but they thought it was like the respondents, when they were asked, they thought it was going to be more like 80% of the time. So I think what happens is you hear me say a few things and they seem reasonable, and you impute reasonable views to me on other things. But on some issues, I'm just flat out unreasonable, and we disagree. But like that you wouldn't know it unless. So I think, I'm sure I have, the views that I have do not seem idiosyncratic to me. They seem completely reasonable. But there's no doubt in my mind that somebody else would say, well, he's a pretty reasonable guy, but I don't know what his issue is about this, because this is just doesn't seem to fit. Because the coherence is just a multidimensional thing, and each of us has our own sets of coherences.
So is coherence that concept that you're describing where it's, I think that my friend agrees with me?
Well, I'm thinking of my own views. So like, I feel like I have a set of views which make sense.
Mm-hmm.
They all make sense. But to an outsider, they wouldn't necessarily look coherent. Like they'll just say like, well, this is weird. He believes all these things. Like, how is it, like I'm a big fan of Tom Wolfe, the author. So someone might say, well, I can't believe you like Tom Wolfe. Like, he says all these ridiculous things. Like, Tom Wolfe went on record as saying he didn't believe in evolution. Well, that's I'm not a fan of that aspect of Tom Wolfe, but like I like The Painted Word and From Bauhaus to Our House. But the art historians hate those books. Like, they must think I'm nuts to like it. It's probably just because I'm ignorant. One of my favorite books is A.J.P. Taylor's The Origin of the Second World War. It's just a beautiful book. I was talking to a colleague of mine in international relations, and I said, is this book all wrong? And he's like, yeah, it's all wrong. So yeah, it's a great book. It's a beautifully written book, but it's just wrong. But it's hard for me to get to that stage of figuring that out. So, well, since he told me it's wrong, I can accept that because he's the expert. But the point is, we just have everyone has a set of views that would seem, but I'm not going to answer you and say, oh yeah, I believe that Oswald didn't shoot Kennedy or something like that. No, I don't have any of those particular views that are kind of way out there.
Appreciate your answer. That was really awesome. Thank you for that. So if you could have a billboard put up anywhere, what would you put on it?
I have a blog, which is kind of like an online billboard, and I put something new up every day. So I guess if I had a billboard, I'd probably put up 400 different messages in a year and have lots of conversations on the billboard. And I'd probably be kind of torn between trying to have a coherent message and having something interesting. So when people drive by, they have something new to see.
So what do you wish you had known when you first started your career?
Everything. I mean, there's so much I understand now better than I understood before. It is kind of frustrating to think. I mean, some of it is just a natural maturation. I remember being a graduate student and thinking it's cool how my advisor can answer all these questions, but now I can answer a lot more questions than I used to, and also I know a lot of tricks to avoid answering questions. Like, someone asks you a question, you talk about something you know about, or they ask you a question, you ask them what they think, or you just move the ball forward a little bit. Oh, I don't know about this, but let me say this general thing. So there are a lot of ways. It's too bad. When you learn tricks like this, it makes your life easier, but then Here, since the Bayesian thing, I feel like the importance of stronger priors and Bayesian analysis, that more and more, like we use uniform priors and then like in our book, and then years and years later, I started talking about weakly informative priors. And other people are talking about that first. I don't think I invented the phrase weakly informative priors, but I think I did a lot in that area. But now I'm interested in stronger priors, and it really makes a difference. A lot of problems I have could have been much more better solved by putting in more prior information right away rather than waiting. So I guess that's something like future me could have told past me, and maybe like it would have been a simple enough message that I could have absorbed it. Obviously you can't like cheat and say, oh yeah, well I would like something that's now known now and wasn't known then. Like I wouldn't have been able to, like the stock market page today, and I could have invested in Microsoft in 1982 or whatever, like that, not like that, right? But stronger priors, sure, like there were people saying that, so I guess I could have thought more about that.
What's something you're curious about at the current moment?
I'm curious about if we can, it's sort of empty to say, like fit bigger models more automatically. Like I just feel like there's a lot of, like we're still spending a lot of time in the weeds of algorithmics, and it's kind of frustrating. So I kind of wondering if we can actually get the fitting to be done more efficiently, whether we'd be able to think more abstractly about the models themselves. That itself is kind of an empty statement, but that's what I'll give you.
So what's a topic, academic or just a research interest topic outside of data science that you think every data scientist should spend some time studying on?
If it's outside, then I wouldn't think that every data scientist should be studying it, right? I mean, it's just got to depend on your own interests. And this came up in these, I've taught in various statistics PhD programs, and I kind of get annoyed because they want everybody to learn certain abstract math. They call it probability theory, but it's really not. It's just super abstract. And I feel like, oh no, if you're interested in that, that's fine. But if you're not, maybe you should learn economics, or maybe you should learn some computer science, biology. But I feel like it's a funny question because sort of by definition, if it's outside data science, I wouldn't see why everybody should learn it.
So what's the number one book, fiction or nonfiction, that you would recommend our audience read? And what was your most impactful takeaway from it?
Well, I was twice interviewed by this website called 5 Books. I don't know if it still exists, but once they asked me to recommend 5 books about statistics and once 5 books about politics. So I'm on record as having 10 recommendations. If I had to pick just one, I guess the book How to Talk So Kids Will Listen and Listen So Kids Will Talk. I found that very useful even before I had kids. It's helped me think about communication. It's interesting. They give a lot of advice. The advice seems very easy to when you read the book, but actually to carry it out can be difficult. But it's not just for talking to kids. It's talking to coworkers and supervisors and students and teachers and everybody else. That was a book. Communication is something that we all have to do.
Who's the author of that book?
Two women wrote it. It was written many years ago.
So what song do you currently have on repeat?
I listen to the radio. We listen to WFUV, so then you hear whatever is showing up. So I don't have a single song. I'm a big fan of REM. Like my kids make fun of me about that. The funny thing was that when I was in my 20s, I went with some friends to an REM concert, and I'd never heard of them. And I wasn't really a big fan of pop music at the time. So we went, and then I went to the concert. I didn't really like it that much. And then I told my friend I think I would have liked it more if I'd heard the songs a few times first, and he was kind of disgusted by it. But now, yeah, I like them. I like it. Well, it's old music now, right? So that's my favorite.
So how could people connect with you? Where can they find you online?
You can Google me, and that's where you find me online. I have a web page, and on the web page we have links to all our books and to my published papers and my unpublished papers. And then we have a blog. The blog has a lot of posts, like here I can check, we have about 400 posts a year. It has 9,000 posts or 10,000 posts and 140,000 comments roughly over the years. So people can feel free to join in. And that would be great. I love when people comment, and I've learned a lot from commenters. I'm sure I spend too much time on it, but I feel it's a good way to communicate and a good way to learn.
So how do you deal with like the negative comments? Do you get any negative or trolly comments?
Not too many. So I rarely delete a comment. It's funny, people think I'm deleting their comments, but actually there's a spam filter, so it catches stuff, and then they think I'm approving their comments, but it's just like this. I go through every day and go check the spam filter, and then people get really upset. Like it's been 23 hours and I haven't checked the spam filter, so like they think that I'm suppressing them. We have not had a lot of trolls. And usually the trolls get bored because people respond to them straight. Every once in a while, I've had people just keep going back, and we did have to delete the comment or to stop them from commenting. I once even emailed someone saying, "Could you stop trolling? And we appreciate," but he didn't, and of course he didn't understand that, so he kept doing it. But mostly it's been pretty good. I mean, I kind of like sometimes people are angry and say stuff I disagree with, and I'm glad that they feel free to do that. I wish there's more of that, really. It's good to know, like, when people are disagreeing. It's a very, obviously, lots of people can't stand whatever you do, and they're out there. So I don't delude myself. It's not at all a representative sample, but I can still learn quite a bit from them. I had a friend who taught psychology years ago. He told me that the trouble with classes is they're usually set up so that the student is supposed to become the replica of the teacher. And he said it's very challenging to not teach in that way. And I do find it challenging to teach. When I teach, I do often feel like I'm trying to make them into being like me. But one good thing about the blog is you can just be pretty open. Like once I wrote something, and more than once, I said, "Here, I saw this paper, I looked at it very briefly, and here are my thoughts." And then people are angry, like, "Why are you giving your thoughts?" And I said, "Well, I said I only read it briefly. Why can't I?" But, I see where they're coming from too. But it's good. I like these kind of open discussions. And somehow the Twitter or whatever doesn't seem to do it in the same way.
Right. Well, I'll be sure to leave a link to your blog post as well, or sorry, your blog as well. I found it to be very insightful, a lot of useful information there. Dr. Gelman, thank you so much for taking time out of your schedule to be on the show. I really appreciate you being here. Thank you.
Oh, it was fun. Certainly less effort than doing real work, so that's a good thing. So yeah, well, thanks for doing that. That was interesting.